Hello everyone and welcome to Learn with Chioma, where we make learning simple and effective. I'm Chioma Adibema and in today's lesson we'll learn Foundation Guide to Organic Chemistry Part 1. Whether you're a university student, a polytechnic student, preparing for WAEC, DECO, JMB, or simply strengthening your chemistry knowledge, this lesson is for you. So, get your notebook ready, stay focused and let's begin. In this lesson, we'll learn what organic chemistry is and why it's important. We'll discuss the definition and scope of organic chemistry, the unique properties of carbon including tetravalency, catenation and multiple bonding. We'll also study the functional groups, identifying homologous series and the basics of IUPAC nomenclature. Finally, you'll learn how to correctly name simple and complex organic compounds and test your understanding with practice questions. By the end of this lesson, you should be able to define organic chemistry, explain the properties of carbon, identify common functional groups, describe homologous series, apply the basic IUPAC naming rules to simple and complex organic compounds. Organic chemistry is the branch of chemistry that studies carbon-containing compounds, especially those containing carbon-hydrogen bonds. It's also defined as the study of carbon compounds, especially hydrocarbons and their derivatives. Originally, organic compounds were believed to be substances obtained only from living organisms. However, scientists later discovered that organic compounds can also be synthesized in the laboratory. Examples of organic compounds are methane, ethane, ethanol, etc. Although they contain carbon, these are not classified as organic compounds. CO2, carbon dioxide, CO. Carbon monoxide, calcium carbonate, sodium carbonate. Note: not all carbon-containing compounds are organic compounds. Organic chemistry covers the study of hydrocarbons, which are compounds containing only carbon and hydrogen. Examples: methane, benzene, etc. Functional groups: these are organic compounds containing atoms or group of atoms other than carbon and hydrogen. Examples are alcohol, aldehydes, etc. Biomolecules: these are chemical compounds present in living organisms. Examples are carbohydrates, vitamin, etc. Synthetic materials: these are man-made organic substances. Examples are plastic, synthetic fibers, etc. Organic chemistry is important in medicine, for the production of drugs and pharmaceuticals. In agriculture, for the manufacture of fertilizers and pesticides. In industry, in the preparation of preservatives, sweeteners and flavor. In our daily life, like soap, perfumes, cosmetics and clothing materials, organic chemistry is important in making these. Carbon is known as the backbone of organic chemistry because of its unique properties. It forms strong covalent bonds with itself and with elements such as hydrogen, oxygen, and nitrogen. Carbon can also form long chains, branched chains, rings, and single, double, or triple bonds. These properties allow carbon to form millions of different compounds, making it the foundation of organic chemistry. One important property of carbon is tetravalency. Tetravalency means that one carbon atom can form 4 covalent bonds with other atoms. This allows carbon to build both simple molecules, like methane, and complex molecules, such as proteins and DNA. Without tetravalency, the enormous diversity of organic compounds would not be possible. So far, we've learned what organic chemistry is, why it's important, and why carbon is the foundation of this branch of chemistry. Next, let's explain another fascinating property of carbon. Another important property of carbon is catenation. Catenation is the ability of carbon atoms to bond with one another to form long chains, branched chains, and ring structures. Carbon does this exceptionally well because carbon-carbon bonds are strong and stable. This unique property is one of the main reasons why millions of organic compounds exist today. Now that we've seen how carbon forms long chain, let's look at another property that makes it even more versatile. Carbon can form not only single bonds but also double and triple bonds. A double bond consists of 2 shared pairs of electrons, while a triple bond consists of 3 shared pairs. Compounds with double bonds are called alkenes, and those with triple bonds are called alkynes. These multiple bonds affect the properties and chemical reactions of organic compounds. Multiple bonding increases the variety of organic compounds that carbon can form. Compounds with double and triple bonds are generally more reactive than those with only single bonds. This makes them useful in the manufacture of plastics, medicines, synthetic rubber, and many industrial chemicals. Multiple bonding is also important in biological molecules and many chemical reactions. So far, we've explored the special properties of carbon. Next, we'll learn how organic compounds are classified. A functional group is an atom or group of atoms that determines the characteristic properties and reactions of an organic compound. For example, the hydroxyl group OH is found in alcohols. The aldehyde group CHO is found in aldehydes. The carbonyl group C=O is found in ketones. The carboxyl group COOH is found in carboxylic acids. Identifying the functional group is essential because it helps us classify and correctly name organic compounds. A homologous series is a family of organic compounds with the same functional group and similar chemical properties. Successive members differ by 1 ch. For example, methane, ethane, propane, and butane all belong to the alkane homologous series. As the number of carbon atoms increases, physical properties such as boiling point gradually increase, while the chemical properties remain similar. Let's look at some common homologous series. Alkanes contain only single bonds and with ane. Alkenes contain a double bond and with ene. Alkynes contain a triple bond and with yne. Alcohols contain the OH group and with oil. Aldehydes and with Al. Ketones and with one. Carboxylic acids and with OIC acid. Memorizing these families will make it much easier to identify and name organic compounds. Aldehydes and ketones both contain the carbonyl group, represented as C=O. The difference lies in its position. In aldehydes, the carbonyl group is located at the end of the carbon chain and the compounds end with Al. In ketones, the carbonyl group is found within the carbon chain and the compounds end with ONE. Although they have similar structures, their chemical properties are different, so it's important to distinguish between them. We've now covered the fundamental concepts of organic chemistry. Next, we'll learn how to name organic compounds correctly using the internationally accepted IUPAC system. Now let's move to one of the most important topics in organic chemistry, IUPAC nomenclature. IUPAC stands for the International Union of Pure and Applied Chemistry. It developed a standard system for naming organic compounds so that scientists all over the world can communicate using the same names. Instead of relying on common names, which may vary from place to place, we use IUPAC names because they are systematic, unique, and internationally accepted. Once you understand the naming rules, you'll be able to identify and name many organic compounds with confidence. The first step in IUPAC nomenclature is identifying the root name. The root name tells us the number of carbon atoms in the longest continuous carbon chain. Here are the first 10 root names you should know. 1 carbon is meth, 2 carbons is eth, 3 carbons is prop, 4 carbons is bot, 5 carbons is pent, 6 carbons is hex, 7 carbons is hept, 8 carbons is october, 9 carbons is non, 10 carbons is dec. These root names form the foundation of every IUPAC name, so it's important to memorize them. After identifying the root name, the next step is choosing the correct suffix. The suffix indicates the type of bond or functional group present in the compound. For example, ane represents alkanes with only single bonds. Ane represents alkanes with at least one double bond. Yne represents alkynes with at least one triple bond. Ol represents alcohols. Al represents aldehydes. One represents ketones. OIC acid represents carboxylic acids. Knowing these suffixes helps you identify the class of an organic compound immediately. Now that we know the root names and suffixes, let's learn the step-by-step rules used to name organic compounds. The first rule is to identify the longest continuous carbon chain. This chain becomes the parent chain and determines the root name of the compound. Remember, the longest chain is not always the straightest one, it may bend or branch, so examine the structure carefully before deciding. Choosing the correct parent chain is the foundation of correct IUPAC naming. The second rule is to number the parent chain. Start numbering from the end that gives the lowest possible number to the functional group, multiple bond, or substituent. This is called the lowest locant rule. It is best to do upper and lower numbering so as to get the side with the lowest sum of numbers. Correct numbering ensures that the final name follows IUPAC standards and avoids ambiguity. The third rule is to identify the principal functional group or any multiple bonds. The principal functional group determines the suffix of the compound. If a double or triple bond is present, its position must also be included in the name. Always identify the highest priority functional group before naming the compound. An alkyl group is formed when one hydrogen atom is removed from an alkane. Because of the loss of one hydrogen atom, the alkyl group now has one free bond that allows it to attach to another atom or group of atoms. Alkyl groups are not usually found on their own. Instead, they act as substituents attached to the main carbon chain of an organic compound. Their names are obtained by replacing the suffix -ane in the parent alkane with -yl. For example, methane becomes methyl, written as CH. Ethane becomes ethyl, written as CH. Propane becomes propyl, written as CH. Butane becomes butyl, written as CH. Pentane becomes pentyl, written as CH. These alkyl groups are very important because they appear frequently as branches in organic compounds. For instance, in the compound 2-methyloctane, the word methyl tells us that a methyl group is attached to the second carbon atom of the main chain. Understanding alkyl groups will make it much easier to identify substituents and correctly name branched organic compounds using the IUPAC system. The fourth rule is to identify all substituents attached to the parent chain. Common substituents include methyl, ethyl, and propyl groups. Each substituent is assigned the number of the carbon atom to which it is attached. If there are two or more identical substituents, use prefixes such as di, tri, or tetra. Different substituents are listed in alphabetical order. Rule 5 is to combine all the information into one complete IUPAC name. Write the positions and names of the substituents first, followed by the root name and the correct suffix. For example, a compound with an OH attached to a 3-carbon chain is named propanol or prop-1-ol. Let's summarize the process for naming branched compounds. First, identify the longest carbon chain. Second, number the chain correctly. Third, identify and locate all substituents. Fourth, arrange different substituents alphabetically. Finally, combine everything into one complete IUPAC name. The more examples you practice, the easier this process becomes. Naming organic compounds is a skill that improves with consistent practice. Excellent! We've now learned the basic rules of IUPAC nomenclature. In the final section, we'll summarize these rules into 7 simple steps, discuss common mistakes, solve practice questions, and review everything we've learned. Before we move to our practice questions, let's summarize the IUPAC naming process into 7 simple steps. Step 1. Identify the longest continuous carbon chain. Step 2. Number the chain correctly and make sure the lowest number is picked. Step 3. Identify the functional group or multiple bond. Step 4. Identify all substituents and note their positions. Step 5. Combine the prefix, root and suffix. Step 6. Use commas in between numbers. Step 7. Use hyphen in between letters. Following these 7 steps consistently will help you name organic compounds accurately. Let's look at some common mistakes students make during IUPAC nomenclature. The first mistake is choosing the wrong parent chain. Always select the longest continuous carbon chain. Another common mistake is numbering the chain from the wrong end. Remember to use the lowest locant rule. Some students also forget to identify the principal functional group, which leads to an incorrect suffix. Another mistake is arranging substituents incorrectly. Different substituents should be written in alphabetical order. Finally, remember to use commas between numbers and hyphens between words. Small punctuation errors can make a correct answer appear incorrect in examinations. Avoiding these mistakes will greatly improve your accuracy. Now, let's test your understanding. Pause the video and try to answer these questions before looking at the solutions. Question 1. What is the functional group of alcohol? Question 2. What property of carbon allows it to form long chains and rings? Question 3. Name the compound with an carbon parent chain and methyl groups attached to carbons 2 and 5. Question 4. What is the name of a straight chain alkane with 5 carbon atoms? 1. The functional group of alcohol is the hydroxyl group OH. 2. Catenation. 3. 2,5-dimethyl-octane. 4. 5 has the root name, pent, and from the question, it's a alkane family. So therefore, the answer is pentane. Let's check your answers. Question 1. The functional group in alcohol is the hydroxyl group, represented as OH. Question 2. The correct answer is catenation. Question 3. The correct IUPAC name is 2,5-dimethyl-octane. Question 4. The correct answer is pentane. If you answered most of these correctly, congratulations. If not, don't be discouraged. Review the lesson and keep practicing. Remember, practice is the key to mastering organic chemistry. Let's quickly recap today's lesson. We began by defining organic chemistry and discussing its importance and wide range of applications. We explored why carbon is unique by studying its tetravalency, catenation, and ability to form multiple bonds. Next, we learned about functional groups, homologous series, and the differences between aldehydes and ketones. Finally, we introduced the IUPAC system of nomenclature and learned the basic rules for naming organic compounds. These concepts form the foundation of organic chemistry and will prepare you for more advanced topics. We've come to the end of today's lesson. I hope this video has given you a solid foundation in organic chemistry and helped you understand the basics of IUPAC nomenclature. Thank you for learning with me today. This is Learn with Chioma, where we make learning simple and effective. Don't forget to like, share, and subscribe. I'll see you in the next lesson. Goodbye.